3 AI agents shared one repository, and they shipped a real game. Now, on to the AI learning.
In this session, we walk from prototype to published, using 3 AI agents in one repository. Through the DDS Vibe Academy, you will access a free masterclass on multi-agent workflow architecture, framed around building a Chopopo quality browser game scheduled to launch in 2026. Our case study artifact is Ashaveth, a fully published grimdark browser RPG. Players choose among warrior, rogue, and mage classes and face 4 progressively scaled boss encounters. We will use Ashaveth's live telemetry and balance data to ground our engineering decisions throughout the loop. Running 3 agents against a single repository creates immediate collision risk. Parallel execution can cause file locks, overwrite errors, and data corruption. The central challenge is orchestration, how to maintain deterministic state so agents never trample each other's work while still moving quickly. To avoid collisions, we adopt an architecture of 3 surfaces. Each agent receives an isolated execution environment with strict boundaries to prevent context pollution and file lockouts. Cowork, Claude Code, and Antigravity each own distinct responsibilities that never overlap in the commit path. Cowork functions as the orchestration and verification layer. It coordinates the agents, runs primary research, and maintains alignment with human intent. Critically, Cowork verifies results in a live browser, ensuring that what ships matches both the written brief and the user experience we expect. Claude Code is our execution and deployment surface. It owns primary source code generation, runs tests in isolation, and performs scoped commits. From this surface, we push final builds to production origins, ensuring that only validated, reproducible changes ever cross the deployment boundary. The Antigravity Gemini agent handles parallel, non-colliding background tasks. It operates strictly outside the main commit path, with absolute file isolation. This design lets us pursue concurrent progress, such as asset generation or long-running simulations, without risking file locks or merge conflicts. Production for Ashaveth was driven by a strict dispatch loop of 26 briefs. Each brief captured a self-contained unit of work. By completing the entire workflow in a single orchestrated session, we maintained momentum, limited context switching, and produced a fully traceable change history. Our briefs favor specifications over suggestions. The average brief was about 3.5 kilobytes. The largest exceeded 9,300 characters. These documents act as dense technical specs, defining architecture, schemas, contracts, and error handling, so agents treat them as engineering constraints, not creative prompts. Spoken prompts introduce ambiguity, which invites hallucinated scope. Written briefs eliminate that risk by enforcing explicit systemic boundaries. By encoding requirements, exclusions, and success criteria in text, we prevent AI agents from inventing features or behavior outside the intended design. Every brief includes the precise write-allow list. We enumerate exactly which paths the agent may modify. Any attempted change outside those paths results in immediate rejection. This explicit path control converts the repository into a governed surface where unauthorized edits simply cannot land. Containment is something we prove, not trust. After every run, agents must show an empty Git diff for excluded paths. These diffs become cryptographic evidence that boundaries were respected. We never rely on an agent's claim that it stayed in lane. We verify that claim through tooling. Guardrails must override convenience. In one run, an orchestrator's trailing command tried to stage 19 unrelated files with gitad A. Even though the new code was sound, the agent rejected the run because it violated the brief's scope, preventing accidental, repo-wide side effects. Infrastructure can silently lie. Our interface reported a successful syntax check, yet Git showed only 183 of 218 lines were committed. The environment had truncated the file, creating a latent defect. This incident underscores why we must inspect actual artifacts, not rely solely on tool output. To mitigate corruption risk, we only commit from the most reliable surface. Corrupted blobs are blocked at a gate, while the native file system agent performs clean, verified commits. This separation of concern ensures that transient or untrusted environments never overwrite good production code. We adopt a principle: verify the artifact, not the interface. File systems, caches, and CDNs can mislead you. Instead of trusting a passing command output, we inspect the actual committed blob and confirm the deployed origin matches expectations in size, content, and behavior end-to-end. Our corrections log surfaced serious issues. A conditional build leaked an API key, and our quota design depended on client-supplied headers. We fixed both by scanning distribution assets and moving to server-generated HMAC-signed session IDs, ensuring clients cannot tamper with enforcement. We reconciled simulations through 2 passes. A broken model dropped the level 50 mage's win rate to 10%. Adding potions and barriers restored a 100% reference in an independent harness. The coding agent's 60 to 72% outcomes then fell within these bounded brackets, confirming balance realism. Security controls are credible only if they fail correctly. We deliberately poisoned a build with a mock key to confirm the guard aborted execution. A non-zero exit code proved the trigger worked. In parallel, a hard global limit of 5,000 requests per day constrained financial exposure. The entire loop, from orchestration to safeguards, is openly available. There is no paywall, sign-up, or certificate gating access. The focus is purely on practical, production-grade work. To follow future loops and deepen your expertise in multi-agent systems, subscribe at DDS Boston.